All right, so we started with sequences. So the technical definition of sequence is basically a function defined from the set of natural numbers to set of real numbers, right? So that's the technical definition. In simple words, a sequence is an infinite ordering of real numbers. Okay, so if I were to define it in words, it's an infinite ordering of real numbers. Okay, so that's a real sequence. Okay, similarly, you can have sequences in vectors. All right, so you could have a sequence in vectors which we call an Vn, where this would be satisfied as v1. So v1 could be a number, let's say 2 comma 3. v2 would be a vector, let's say 2.5 comma 3.5. v3 could be a vector, let's say 3 comma 4. v4 could be something, so and so on. So it's an infinite sequence in vectors where each element is a vector. You could have infinite ordering of uh, complex numbers and so on. So the list goes on, but we are mostly interested in real numbers, sequences of real numbers, because once we know the properties of sequences of real numbers, we can basically apply it on vectors of real numbers as well. And complex numbers, all those things are not in our syllabus anyway, so we don't. Like I told you, the important thing for sequence is to understand where is the sequence heading. Okay, where is it heading? So what is the limits of these sequences? What are the limits of the sequences? So suppose I give you a bunch of sequences. Suppose this is uh, the rate of interest. Suppose there's a sequence of vectors v, which is basically uh, interest in bank 1 and interest in bank 2. So there are two banks which are offering different interest rates. Now interest in, so this sequence basically looks like this. Okay, so this bank starts with an interest of 7, this bank starts with 5. Then this becomes 6.9, this becomes 5.1. So this is in time period 1, this is in time period 2. Then it becomes 6.8, 5.2, and so on it goes. Okay, so it follows the pattern. So I hope you can see the pattern now. Okay, the pattern is the bank 2 interest rate, it keeps increasing by 0.1, bank 1 interest rate keeps reducing by 0.1. So you see, after some time, what will happen is that after some years, I2 will become greater than I1. So suppose you're a person who's investing 10,000 rupees every month. So initially you will keep investing in bank 1 because bank 1 is giving higher interest rates. But after some time, you'll start investing in bank 2. So after what time do you start investing in bank 2? So that will come from the prediction about how these sequences are heading. So this is why being able to predict the pattern of sequences is important. Uh, now, generally, this sequence after 10 iterations, this would become 6 and this would become 6. So after 10 iterations, t equals to 11. These both will become equal. After that, this would become 5.9, this would become 6.1, and so on. So after this, we'll start investing in that. So these sequences, we are not interested in the infinity of them. We are only interested in the finite horizon thing, that what happens after 10 periods or 100 periods or so. But when we talk about math, in math, we are going to look at what happens to the sequences when it goes to infinity. So that is going to be the limit of a sequence. So limit of a sequence is basically the value which the numbers take at infinity. Okay, so when after a long time, what is going to be the value of these numbers? So that is limit of a sequence. So let's look at the technical definition. So the technical definition could be a little more complicated. But if I were to explain it in words, I'll say, suppose I'm saying that the limit n tending to infinity of some sequence xn, this is equal to n. So what does this mean? This means that as as this subscript n, it goes to infinity, the sequence element xn, we say that at infinity, this xn is equal to L. It means what? It means that these the sequence, wherever it starts from, it could start from here or it could start from here, wherever it starts from. After some point, all the points are going to be around L. So basically, after some points, all elements of the sequence xn are going to be around L. Not necessarily at L, okay, not equal to L. They are going to be around L. Now, this around L is a very vague term. Which vague? What is around? Like, what is around? Okay, so you can say that I stay around Shah Rukh Khan's home. Like, how do you define around? Like, what is around? Like, is your neighbor? You're sharing a boundary with him? Or are you living in Bandra? Are you living in Mumbai? Are you living in India? Are you living on Earth? Like, how do you define around? Around could be anything. For an alien civilization, around would mean that you are living maybe in the same galaxy as Shah Rukh Khan. So the around word has a very vague connotation to it. So we cannot rely on this definition in math because math has to be absolute. It cannot be vague. Okay, so the technical definition of limits of this around thing is something like this. Okay, now this definition is something which is going to be new, but similar definitions are going to follow later on. So we'll spend some time with this definition, seeing what it means. So sequence converges to a limit x. So this is written as limit n tending to infinity xn is equals to this number x if for every epsilon greater than 0. Okay, so let me draw a figure here that would be easy. Okay, so let's say the element, this is n equals to 1, 2, 3, 4, 5, 6. Suppose, and this is their xn values. So for n equals to 1, let's say this is this, and so on. So these, the sequence is, let's say, going up in this manner. It looks like a logarithmic curve. Okay, it's going up. So if I were to connect these dots, the sequence numbers would probably look something like this. But since it's not a function sequence, it is not defined on all points. It is only for n equals to 1, n equals to 2, n equals to 3. Okay, so this is your x1, this is your x2, and so on. Okay, so I'm not writing everything because it will become very cluttered. You won't be able to draw anything from the graph if I put everything in. So I'm keeping it as neat as possible. So we say that the limit of this sequence is x if for every epsilon greater than zeros. So what is epsilon? Epsilon is some degree of aroundness. Okay, so I told you this word around is vague. So now we are defining this around thing. So we are saying take any aroundness you want. You want it to be, you want the distance to be uh, 10 kilometers, you want it to be 10 meters, you want it to be 10 nanometers. Okay, so this epsilon could be 1000 or it could be 10 to power minus 1000. I don't care. As long as it is positive, I'm okay. You can define this aroundness as much as you want. I don't really care about it. The point is that for every epsilon, you can find a natural number n such that all elements xn after this point capital N will lie around my limit. So what this means is you take some epsilon around x. So this is my x. So you take any epsilon around x. Okay. So for this epsilon, you can find a natural number. Let's say this is n equals to 100. Okay, so after this n equals to 100, what I'll see is that this is too long. After this n equals to 100, what I'll see is that all elements of the sequence, they will lie in this epsilon neighborhood. This This point is x plus epsilon to x plus epsilon to x minus epsilon. Now, this epsilon is basically the sense of aroundness that I was talking about, which was vague. It is still vague, but it is open-ended. Like you can take any aroundness as you want. You can take it as large as possible. You can take it as small as possible. Okay, you can go epsilon like this, or you can take epsilon so small. The point is that maybe this n will change. If you take epsilon smaller than before, maybe I'll have to stick with a much higher natural number, let's say thousands. But I can say for sure that after 1000, all elements will lie in this band. Okay, so this is what I'm saying. So let us look at an example to understand this thing. Okay, so let me copy the statement. Okay, so the statement says that limit n tending to infinity xn is equals to x if for all epsilon greater than 0 there exists a natural number such that mod xn minus x is less than epsilon. Okay, so this is the definition. So what is the example that I'm going to take? Example I'm going to take is I'm going to take some sequence. Let xn be equal to 1 by n. Okay, so this sequence will basically look like 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, and so on. Okay, so let me ask this question to Ananya. So Ananya, where do you think this sequence is headed to at infinity? What is the limit of this sequence, Ananya?
So I think there will be no limit. Up to infinity it will be there.
No, I'm not asking that is it going to be infinity. What will be the numbers look like? Where are the numbers headed to? Suppose this was, let's say, the inflation rate in some country.
Upon x, it will be like x upon x plus 1.
No.
So will it be 0?
Yeah, it will be 0. It will be 0. Yeah. Thanks, Kritika. So after some time, this thing is heading. It keeps going down and down. It keeps getting smaller and smaller in magnitude. So it is tending to 0. Important thing to note is that this is never 0. This is never 0. Okay. 1 by n is never equal to 0. We are saying that 1 by n is tending to 0. Okay, we are not saying that it is equal to 0. We are saying that it is tending to 0. Okay, so what we are essentially saying is that limit n tending to infinity 1 by n should be equal to 0. Okay, what is the meaning of this? It means that it should satisfy this equation. So let us draw a graph to represent these numbers. So if I were to draw some graph, okay, so these numbers, they'll basically start looking like this. Okay, so at 1 it will be 1, at 2 it will be half, then 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 8, 9, and so on. So it will start getting closer and closer to this x-axis, but it will never get equal to this x-axis. Right? It gets closer to the x-axis, but is never going to touch your x-axis. So now I want to test this this definition. So this definition says that for every epsilon greater than 0, mod xn minus x should be less than epsilon. So basically, I'm assuming I have this intuition that the limit should be 0. So I'll start focusing on 0, and I'll construct an epsilon band around 0. Let me also extend this a little bit below. Okay, so now what I'll do is I'll construct some epsilon band, which is basically my degree of aroundness. So let me ask someone, let me ask Anuradha, give me a epsilon greater than 0, whatever you can think of, but think small. Don't think 1000, 100. Think like something less than 1, because this is 1. So think something in this range. So give me an epsilon. Any real number.
Sir, 0.1.
0.1. Very good. Okay, so let's say epsilon is 0.1. So this point would be 0 plus 0.1, and this point will be 0 minus 0.1. So I want to find a point n after which I want to find a natural number such that after n, all elements of this sequence are going to be inside this range. Okay, all the blue dots should be inside this yellow range. Okay, so I want to find n such that 1 by n should be less than 0.1 for all n greater than 10. Okay, so let me ask this question to Kanishka. Can you give me a capital N such that for all small, just tell me what value of small n will this be?
So for 5, so because for 4,
So 1 by n less than 0.1.
so 1 by 5.
No, this is 0.1.
Oh, sorry. 1 upon 11.
Rearrange it from this.
1 by 11.
Yeah, very good. Okay, so this means that n should be greater than 1 by 0.1, right? When you rearrange this, so this just becomes n greater than 10. So n greater than 10 is 11, right? So you can take 11 or you can take 1000. I don't care, as long as it is greater than 10, it will satisfy. So you can say that after this point, all elements will be in this yellow range, or you can say that after this point, all elements will be in this yellow range. The question is not finding the exact point. This is not the question. The question is, does there exist such a point that after that point, all elements lie in this particular yellow point, this band, this epsilon band, everything should lie in this epsilon band. That is happening for any n greater than 10. Now I can choose another epsilon. Okay, so Anuradha gave me an epsilon of 0.1. Maybe I'm not happy with it. So I take an epsilon of 0.01. Okay, so let me ask this question now to Kashish.
Yes, sir.
Yeah. So the question is that for epsilon 0.01, this thing becomes 0.01. So can you give me a n for which this thing will be true? Can you give me a small n for which this thing will be true?
So 100.
Very good. Very good. So for n greater than 100, it will be true. So you can say n greater than 100. Okay, n should be greater than 1 by 0.01. So that is 1 by 100. Or you can say n greater than 1000 or 10,000. As long as it lies in the yellow band, I don't care. Now this will work for every epsilon. You see that the thing is, the statement says for all epsilon. Okay, so you can give me an epsilon as small as you can imagine. I can give you a capital N after which everything will be in the yellow band. You can make the yellow band smaller. I'll push N forward. So it will keep happening. And that's why we say that this limit is 0. That is the meaning of this limit being 0. So this epsilon is the degree of aroundness, which I was talking about, which is vague, but now we have defined it. I'm saying that take your definition of aroundness. Whatever your definition of aroundness is, I will find numbers around n. Okay, so that is the definition of that of limit. So let us work with some other example now. Is this? Yeah. So example now is minus 1 by n. So the terms are going to be -1, -1. Oh, no, not sorry, not -1 by 1 by -1 to the power n into 1 by n. Okay, -1 to the power n. So the terms are going to be, when you put n equals to 1, this becomes -1 into 1 by 1. When you put n equals to 2, this becomes -1 square into 1 by 2, -1 cube into 1 by 3, -1 4 into 1 by 4, and so on. So this is just -1. -1 square is 1, so 1 by 2, -1 by 3, 1 by 4, and so on. So this is my sequence. So my question is that what do you think the limit of this sequence is going to be? It's an open question, anybody can answer.
It will also be, it will also tend to 0.
Very good. It is also tending to 0. So one good way would always be that you can basically draw the numbers and see where they are heading. Okay, so you can draw it. -1 is here, -half is here, -1 by 3 is here, and so on. So they are getting closer and closer to this 0 thing. Now, if I want to test it, what I can do is I can build a band around 0, an epsilon band around 0. And you can check if everything is inside this epsilon band or not. So you see that, yes, after some point, everything will lie in this epsilon band. Now you can make this band as small as possible. Okay, you can go with a smaller band. You can keep reducing the value of epsilon. So for this epsilon, after this point, every point will lie inside the band. So this band, it contracts as your epsilon reduces. So as you reduce your epsilon, the band will keep on contracting. But the important thing is that even if the band contracts, you can push the boundary further and still find all numbers inside this epsilon. So for this case also, we say that limit n tending to infinity xn will be equal to 0. Okay. So if the sequence has a limit, we say that it is convergent. If it has no limit, we say that the sequence is divergent. So for example, consider the sequence xn equals to n, which is basically going to be 1, 2, 3, 4, 5, and so on. So my question would be to Vinay, what would be the limit of this sequence? Where do you think this sequence is headed at infinity?
So to infinity.
Very good. It's going towards infinity. There is no stopping this sequence. It's on increase. Like there's no tomorrow. So this one will have no limit. Okay. Then we can have so similarly you can basically start analyzing sequences now and see if they do have some limit or not. So the next proposition, I'm not going to do the proof of this thing, although I've given the proof using triangular inequality. I'm not going to do it like this. I'm going to give you a graphical interpretation of why it's true. Okay, so we say that the limit of a sequence, if it exists, is unique. Okay, so the statement is that the limit of a sequence, if it exists, is unique. It means that if the sequence has a limit, there will be only one limit. You cannot have two different numbers as the limit of that sequence. So let's prove this by contradiction. So how do I prove by contradiction? So the proof will work like this, that assume the contradiction of this. So assume that a sequence has two limits. So the statement says कि अगर limit है तो उसकी एक ही limit, उसकी दो limit नहीं हो सकती. So we are saying that, okay, so let's assume that there exists a sequence which has two limits. Okay, what are the two limits? The two limits are going to be, let's say, x1 not equals to x2. So these are the two limits of my sequence. Okay, so let's say the two numbers, they are like this. Okay, so this is my x1 and this is my x2. Okay, now since they are not equal numbers, they are different numbers, they are not going to be on the same point, they are going to be on different points. Now the idea is that the sequence, it could look something like this. Okay, so it could maybe look something like this. Okay, I don't know what it looks like. I'm just randomly drawing some sequence. So I feel that it might look something like this. So you can now draw two bands, one around x2 and one around x1. Increase the thickness of these bands. So this is a sequence around x2 and this is a sequence around x1. So as you can see that after some point, yeah, some elements lie inside this band. After some point, some elements lie inside this band. So let's say this number is n1, this number is n2. So, but you see, there is going to be no band which is going to contain all the numbers. Right? I don't know what this sequence is like. Maybe half of the numbers are here, half of the numbers are here. But still, what I want is that everything should be in this band after some point. Now, since these bands, they don't coincide because I have constructed these bands in such a way that they don't coincide. I don't care how close x1 and x2 are. So you can take x1 equals to 1 and x2 equals to 1.001. I can still construct epsilons in such a way that these bands are not coincidental. You can take epsilon equals to 10 to power minus 10, in which case the figure will look something like this if you zoom into the graph too much. If you could maybe zoom into the graph 10 times, sorry, 10 to power 10 times, you would actually see something like this, that x1 and x2 are too far apart, and the epsilon bands don't coincide. So now what I'm saying is that after n1, everything should lie here. After n2, everything should lie here. Which means that if n2 is greater than n1, then what I'm saying is that after n2, everything should lie here as well as here. This is not true. A number cannot exist in two different sets simultaneously, two disjoint sets. Okay, these are two different bands. A number can only exist here or it can exist here. So what I'm saying is that after some point, everything should be in blue region, and after some point, everything should be in green region. But both these statements cannot be true simultaneously. It's like saying that everybody over the age of 40 years should live in houses, but everyone above the age of 60 years should stay in buildings. Okay, then you are imposing two sorts of conditions on everybody who's above 60 years, that they should live in houses as well as in buildings. So that's not possible. Okay, as long as houses are not buildings, houses are single roof houses. All right, so this is the working definition. I don't need this proof. I just wanted you to know that two limits don't exist. So we can see an example of a format where sometimes people make a mistake, and this is in fact a question from past year. So they give the limit xn equals to -1 to the power n. So this sequence becomes basically -1, 1, -1, 1, -1, 1, and so on. So a lot of people tend to write that this sequence has two limits, -1 and 1, but that is not true. Okay. Why is that not true? Because yeah, you can construct these two bands and you can say, suppose this band is 1 and this band is -1. You can say that yes, after some point, half the numbers are here and half the numbers are here. In fact, from the beginning itself, half the numbers are here and half the numbers are here. But I don't want half the numbers here, half the numbers there. I want everything in one band. And that is not going to happen. So this sequence, this has no limit. That is the correct thing. So if it has no limit, it means that it does not converge. You cannot expect such easy questions right now, by the way. I mean, these were old times, good times when they used to ask easy questions. They don't ask it anymore. Now another example, n cube goes to infinity, so does not converge. Where is this? Yeah, this is another example, 1 by n. Sorry, this should be 1 by 4. Yeah, so we already discussed, so this goes to 0. -1 to power n does not converge. We don't say that it has two limits. Okay. Now there's some more definitions. A sequence of real numbers is bounded from above if there exists a real number capital M such that all elements are less than equals to M. Okay, so we are saying that a sequence xn is bounded from above if there exists some real number M such that M is greater than or equals to xn for all n. Basically, I'm saying that there should be some number which is greater than every element of this sequence. Okay, so let's take some examples. Suppose I take xn equals to 1 by n. So I know that 1 is greater than or equals to 1 by n for all n. So 1 is definitely an upper bound. You can take 2 as upper bound, 3 as upper bound. You can take 3.5 as an upper bound. 0.5 is not an upper bound. Okay, an upper bound is something which is greater than every element of a sequence. So here 0.5 is not an upper bound because 0.5 is less than 1, which is a valid term of this sequence. So we say a sequence is bounded from above if all elements are lower than something. If there exists some number which is greater than every element, then we say that the sequence is not going to infinity. Okay, so if a sequence is not going to infinity ever, then we say that it is bounded. Another example could be -n. So -n is basically -1, -2, -3, -4, and so on. So this thing is also bounded from above because you can find a number which is greater than every element of the sequence. Right? So Asma, can you tell me a number which is greater than all these numbers? Any real number greater than all these numbers? All the numbers of the sequence, actually. Hello, Asma, can you hear me? Okay, maybe she is unavailable. Okay, anybody else wants to take up that question? Any number greater than all these numbers?
So 0.
0 is greater than all these numbers. These are all negative numbers. So you can say 0, you can say 100, you can say 0.5 also greater. Minus 0.5 is also greater. I don't care. As long as there's even one number which is greater than all these numbers, this sequence is bounded from above. All right. So that's the definition for bounded from above. A sister thing is bounded from below. So you say a sequence is bounded from below if there exists small n belonging to real numbers such that small m is less than or equal to xn for all n. Basically, it should not be going to negative infinity. That's What I'm saying, this in this very technical manner, what I'm saying is that this sequence should not be going to negative infinity. If it is not going to negative infinity, it is bounded from below. So let me call this example 1. This is example 2. So Anuradha, can you tell me which of these sequences is bounded from below? Sequence 1 or sequence 2?
Sir, sequence 2 is bounded, not bounded below, because it will goes on -5, -6, and so on.
Yeah.
And sequence 1 is yes, sir, it bounded below because it doesn't go down like
Very good. Perfect.
below the
Perfect.
zero.
Perfect. Yeah, it doesn't go below 1 actually. Below 0 actually. It never goes to negative territory.
Yes, sir.
So this sequence is bounded from below, but this one is not bounded from below because it's going to be negative. So you can never find a real number which is lower than all the numbers. You
Yes,
give me
sir.
m equals to -10 to power -10, I can still find a number which is lower than that. Eventually it will happen. Thank you, Anuradha.
Yes, sir.
Okay, so that's how this thing works. Okay, so bounded from above, bounded from below. Now, if it is bounded from both sides, then it becomes a bounded sequence. So we say a sequence is bounded. Okay, so this is xn is bounded if it is both bounded from above and bounded from below. So it should have some bound above and some bound below. Basically, it should not be going to positive or negative. Okay, so next question would be Ananya. Which of these sequences is bounded?
So first one, it is that limit is 1 and 0.
Yeah, very good. So one is bound because it is going neither to positive or negative infinity, but this is not bounded because it is going to negative infinity. So it has a bound above, but below it has no bound. So bounded sequence is one which has both an upper and a lower. Okay, so that is important. Okay. So the sequence n cube is bounded from above, but not from below, obviously. Right. The sequence n cube, it will look like this. So nothing goes below 0, below 1 actually. So this has a bound below. -1 to power n plus 1. This is also bounded. Okay, so it goes nowhere. -1 to power n plus 1. It will be -1, 1, 1, -1, and like this. Okay, so this has bounded above as well as bounded below. So this is bounded. A convergent. So the next proposition is that a converger sequence is bounded. So what I'm saying is that if a sequence is convergent, it has to be bounded. It cannot be unbounded. Okay, so I'll come to the proof of this thing, but first you need to understand what I'm saying is that if this is the set of all sequences in the world, okay, and this is the set of all bounded sequences in the world, okay, so this is all bounded sequences, then the set of convergent sequences, it would be this. Okay, so this is going to be the set of convergent sequences. Okay, so all convergent sequences are bounded, but there are possibilities of bounded sequences which are not convergent. Like I told you, -1 to the power n plus 1. This is basically 1, -1, 1, -1. So this thing is not bounded, but it is, sorry, this thing is bounded, but it is not convergent. So it lies somewhere here. Okay. So the set of convergent sequences is a subset of bounded sequences. Right, so how do I show this? How do I show this? So showing this is very straightforward. So for that, I'm assuming, again, you prove by contradiction. Or you don't actually need proof by contradiction. You can work directly also. Let's work directly. So what I'm saying is that there's some sequence which is convergent. So if it is convergent, it will have some limit x. So basically, if it has some limit x, then the definition tells me that after some point n, all elements of the sequence should lie in this band, right? So all these elements are definitely bounded. So let me call this as set S1. So set S1 is all the elements of the sequence after some point capital N. Okay. The points before it, they could lie outside the belt. So let me call all these elements as set S2. So my entire sequence S is basically the set S1 union S2. Okay. Now S2 is a finite set. Why is it a finite set? It's a finite set because it is all the elements before capital N. Now capital N is a number, so all the elements, so it could be 100. So if n is 100, this S2 set has 99 elements in it. If n is 1000, this has 999 elements in it. If it is 10,000, this has 9,999, and so on. Whatever it is, I don't care. It is always going to be finite. Now, a finite set cannot go to infinity or negative infinity. It could be very large, but since the number of elements is finite, it can never keep on increasing or keep on decreasing. Right? So maybe there's a maxima here, capital M, M2. Capital M2 is the maxima, small m2 is the minimum. So let's say capital M2 is the maxima of these finite numbers. Sorry. And small m2 is the minima of these finite numbers. This is capital M2, this is small. Similarly, S1 is a finite set, is an infinite set, but it is lying inside the band. Okay, so in this band, the max you can go is x plus epsilon, and the minimum you can go is x minus epsilon. So the max for this set is x plus epsilon, and the minima for this set is x minus epsilon. Okay. So basically, to club everything that I've done till now is the set S1, which is this infinite set, all elements in set S1, they are going to be inside the interval x minus epsilon to x plus epsilon. And all the elements in set S2, which is finite, are going to be between capital M2, sorry, small m2 and capital M. So the maxima of the bigger set S, which is the combination of all these elements, the maxima of this set will always be less than or equal to max of x plus epsilon comma m2. So there are two sets. One set has a max. So I suppose I just give you two sets. Okay. Okay. Set 1 has max entry 10 and set 2 has max entry 100. So I know that if I take a combination of these two sets, then max has to be equal to 100. So that's what I'm doing. I'm saying that the max of the union of the two sets has to be either x plus epsilon or m2. One of these things. So are you understanding this? Has everybody understood it till this point? I hope there are no doubts. Okay, so the max is going to be between these two. Yeah. Did anybody have a doubt? If you have a doubt, you have to ask me. Yeah, I'm not going to ask you again and again. So the max will be between x plus epsilon and m2. Similarly, the min of the bigger set will be less than or equal to min of x minus epsilon comma small m2. So there's a definite maxima, which is a real number. There's a definite minima, which is a real number. And that's why this set S, it will not go either to infinity or to negative. Okay. So this means that this, whatever is the minima of these two numbers is going to be a lower bound. And whatever is going to be the maxima of these two numbers, this is going to be an upper bound. So if the set has an upper bound, like something which is like a ceiling. So if the sequence has a ceiling, it has a floor, then it is basically sandwiched. It cannot go to infinity or to negative infinity. So it's going to be yeah, it's going to be a bounded set. It's going to be a bounded set. All right, so a convergent sequence is bounded. So it is stuff like this which could be asked directly in DAC exams. So DAC loves things like this, nitty-gritties. Okay? So they might ask you. So if say, like in true false kind of thing, like how many of the statements are true? Questions like that can happen. Now, next example is changing a finite number of elements of a sequence never changes its behavior. Okay, so suppose I change, let's say 10 or 15 elements, it will never change what happens to the sequence at infinity. So the limit is always about what is happening at infinity. So if you change a finite number of elements, it will not change its behavior. It will not change its limit. So the limit does not change with a finite change in elements. So suppose the sequence is 1 by n. So I start with 1 by n. So the sequence is 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, and so on. I'm changing a few terms here. So I don't like 1 by 2. I remove it to get 100. I don't like 1 by 5. I remove it to get 750. I make a few changes like this going forward. But what happens at infinity will not change because of this. Okay, at infinity, it is still going to sleep. So a finite number of changes will never cause the sequence itself to change. Okay, so the sequence xn is defined by the following formulas for the nth term, right? So these are some problems for you to do. These are very easy problems, just writing down the terms of the sequence, nothing complicated. Okay, so you can work it out on your own. Let me move to the next topic, that is properties of limits. So we are going to look at some simple properties. So monotonicity, if xn and yn are convergent sequence and xn is always less than equals to yn, then the limit of xn is also going to be less than or equals to limit of yn. Yeah. Then limit of xn is also, sorry, this should be less than equals to. There's a typo here. Less than or equal to limit of y. Okay, so limit, if xn is always less than equals to yn, then limit of xn has to be less than equals to limit of y. Now the sandwich theorem is important. So the sandwich theorem says that suppose xn and yn are convergent sequences of real numbers with the same limit capital L, and zn is a sequence which is always contained between xn and yn. So what it says is that zn also has the same limit capital L. So let me explain this with the help of a graph. So what it's saying is, let me copy this statement itself. Okay, so what is the sandwich theorem telling me? It's telling me that suppose, first of all, that there are two sequences which have the same limit. So let me consider a sequence xn and another sequence yn. So xn is always less than equals to yn, but the limits are same. Okay, so the limit point is same. Let's say this is the limit point. This is the limit point L. So what it means is, let's say these are my points in Xn. Let me draw Yn first. Yn is the largest sequence. So let's say these are my points in Yn, which are heading towards capital L. And these are my corresponding points in Xn, which is always less than Yn. But it is also heading towards N. So both these sequences individually are heading towards N. But you see that for any given value of N, the blue dot is always lower than the green dot. That is what is the meaning of Xn less than equals to Y. Okay, so for any level of n equals to 1 or 2 or 3 or whatever these other numbers are, the blue dot is always lower than it equals to Y. Now, if you construct a new sequence which is sandwiched between these two sequences, suppose the red sequence Zn is between these two sequences. I should take this. So let's say Zn is a sequence for which elements are always sandwiched between the green and blue dots. Then the only possibility for this red sequence is that it should also have a limit at 10. There's no other possibility. It is strictly sandwiched between the green and blue dots. So the red dots also have to go to L. So this is the sandwich theorem. So sometimes sandwich theorem gets important. Why? Because suppose you cannot find the limit to the red sequence. So what you do is you build a green sequence and you build a blue sequence such that the red sequence is always between these two. And then you show that both the green and blue sequences are heading to the same limit. So that automatically proves that the red sequence also has to go to the same limit. I have never encountered any question in past years from sandwich theorem. So I have stopped giving examples. The point is that we don't want to do too complicated examples. But it's still important to know that there exists some theorem like this, a sandwich theorem, which says this. It just builds our knowledge about sequences, but we will not do any problems from it because it's not really that important. From examples. An example is, so this is not an example of a sandwich theorem. This is an example where the sandwich theorem is not applied. So my question to you would be, why is the sandwich theorem not working in this case? So let us look at this example. So the example is the Xn sequence is -1 and Yn sequence is 1. Okay, so let me draw a new graph. So the sequence Xn is -1 and the sequence Yn is 1. Okay, so this is my sequence Yn, which is constant at 1. And another sequence Xn, which is constant at -1. Okay, 1 and minus. Now another sequence Zn is sandwiched between the two. Zn is -1 to power n plus 1. So Zn basically looks like this. So it is always sandwiched between Xn and Yn. Yet we say that limit Zn n tending to infinity does not exist. Why do we say that?
So because these two sequences are themselves not converging to one point.
Okay, so Kanishka says that because Xn and Yn are themselves not convergent to the same limit. So what she's basically saying is that the limit of this thing Y and the limit of this thing X, they are different. Y is basically 1, X is basically -1. And that is the reason why. That is actually correct. So X and Y, the limits, they have to be same. Only when X and Y are same do we have the sandwich theorem applicable. So here the sandwich theorem itself is not applicable because one of the conditions was that when you're sandwiching, the two bread sequences should have the same limit capital. So this is not happening now. That's why Sandwich Theorem is not even applicable. Okay, next few properties are very easy. Linearity properties. So if you multiply all elements by C, the limit gets multiplied by C. If you add two sequences, the limit of the combined sequence is just summation of individual limits. And if you multiply two sequences, then the limit is multiplication of two. Okay. So these are some simple things. Now my question is, addition diya, multiplication scalar diya, multiplication diya. But I did not talk about limit n tending to infinity xn upon yn is equals to x by y. This thing is not true. Why do you think this thing is not true? Not necessarily true. I should say not necessarily true. So let me ask this to Kritika. Kritika, why do you think this thing is not necessarily true?
So because if xn is less than yn, then it will tend to different limit, and yn is less to xn, then it will tend to different limit.
No, it's not really the case.
Sir, if the limit of y tending to yn tending to infinity becomes 0, then this x by y will
Yeah.
become undetermined.
Yeah,
Not
very
defined.
good. Okay. Yeah, so it is completely possible that yn becomes 0. Not just that, any of the elements could be 0. Okay, right? I mean, even if the limit is not 0, like I told you that you can change a finite number of elements to it. So you can basically change a few elements and make them 0. Right? Even in that case, xn by yn, the term itself becomes undefined. So that's why I don't like zeros in denominator. So there should be no 0 here and there should be no 0. So when there is no 0 anywhere in the denominator, then this is true. Otherwise, it can lead to a difficult situation. That's why we don't say that this general thing is true. Okay. So good. Yes, sir. Thanks. Next up, we have monotone sequences. What are monotone sequences? The monotone sequence of real numbers converges if and only if it is bounded. So this is an important theorem, but it applies to monotone sequences. The word monotone means it keeps on increasing or decreasing. So if a sequence only keeps on increasing or it only keeps on decreasing, it is called monotone. And plus, if the sequence is monotone plus it is bounded, then it has to converge. So the idea is that suppose I have built a bounded sequence. Okay, so there's some sequence which is bounded between these two limits. Okay, this is capital M upper bound, small m lower bound, and the sequence necessarily has to be between these in this band, in this small band. Now, if it is monotone, it can either be increasing only. It cannot go beyond this because this is an upper bound. So I'm saying that it cannot go beyond this. And if it is decreasing, it can look like this. So in either of the cases, what's happening is that it has a limit. In this case, its limit is this. In the other case, its limit is this. Whatever the limit is. Point is, yeah, it need not be m, by the way. It need not be m. Very well, your red sequence could very well be this, in which case the limit becomes LR, limit of the red sequence. It will be some value less than capital M. That's not the point. The point is not what's the limit. The point is that there exists a limit. So this is a very important theorem which says that a monotone bounded sequence is convergent. So if it is monotone and it is bounded, it has to converge. That is no other way to do this. You cannot have a sequence which is non-monotonous. You cannot have a sequence which is monotonous and bounded, but does not converge. You cannot build. Okay. So a lot of times, if we are looking, looking for a sequence that is convergent or not, we try to show monotonicity and we show boundedness. We show this to property, it automatically implies convergence. So if I were to write this in logic terms, what it would mean is monotone and bounded implies convergence. Monotone and bounded implies convergence. So let us look at the most popular example for this. This is 1 plus 1 by n convergence. Now, when I look at this particular sequence, 1 plus 1 by n to the power n, the thing is, as n increases, what happens to the thing inside the bracket? Will it increase or will it decrease? As n increases, what happens to 1 plus 1 by n?
Sir, it decreases.
Very good. Yeah, it decreases because 1 by n decreases. 1 is constant. So this would be like 2, then 1.5, then 1.33, and so on. So it's decreasing. At the same time, there's an n as an exponent. So the impact of the n on power is that as n increases, the entire function increases. So these two things are taking this function in opposite direction. The n inside wants to drag it down, whereas the n above wants to take this sequence higher. So I cannot resolve these two forces with the naked eye. Just by looking at it, pehli baar maine dekha and I'm like, one thing is going here, the other thing is going here. So I can't say for sure that which of these forces is going to be strong. Right. So, so here I'm going to, what I'm going to do is I'm going to basically expand this particular sequence using the binomial theorem. Now, binomial theorem will do this in PNC if you have not done this before. But the way this works is basically summation. So binomial theorem basically says that summation a plus b to the power n should be equals to nc is equals to no, a plus b to the power n should be equal to summation ncr a to power r into b to power n minus r for r going from 0 to n. Okay. Now, what is NCR? NCR is not rational capital region. This is n factorial upon r factorial into n minus r factorial. Okay, so these are things from PNC. Maybe you've done it in your school, maybe you've forgotten about it, maybe touch upon the topic. We'll do it in slightly more detail when we reach permutations and combinations, but I don't want to delve it into this right now. So I'm not going too much into what this is, but this is how you get the expansion of a plus b whole square. A plus b whole square equals to 2c0. Right? If I expand this formula, 2c0 into a to power 0, b to power 2 plus 2c1 into a to power 1, b to power 1 plus 2c2 into a to power 2, b to power 0. So this power zeros, they cancel. Power 1's irrelevant. 2c0 is 1. 2c2 is 1. So what I'm left with is b square plus 2ab plus a square. So a square plus 2ab plus b square. So that is your expansion for a plus b plus. So this is basically your binomial expansion. Binomial expansion is not the important part of the thing that I'm going to do right now, but since I go from here to here to here, I wanted to establish what this is. So here I just expanded this using the binomial theorem. Okay, So this you call as A, this you call as B. So A ki power is 1. 1 to power anything is 1. So it's basically 1 to power n minus k, which is already 1. So it has been omitted from this equation altogether. 1 to power anything is always going to be 1. So it's immaterial. The other 1 by n power k is written and nck is written. After this, what you do is you expand this summation. When you expand this summation, you write all the NCKs. So these are the different NCK values. Okay, now let's focus on these terms. Okay, let me just highlight the terms for you to focus on. These are the different terms I want you to focus on. 1 plus this thing become 1. So 1 plus 1 is 2. So this thing goes here. Right. N into n minus 1 by 2 factorial into 1 by n square. So 1n cancels with this 1n. This becomes n minus 1 upon 2 factorial. So this thing would become 1 by 2 factorial into n minus 1 by n, which is basically 1 by 2 factorial into 1 minus 1 by n. So that's what written. Okay. In the third bracket, what I'll get is this n and n will cancel. What I'll be left with is 1 by 3 factorial into n minus 1 into n minus 2 upon n square. So n square can be broken as n into n. So you can really write this in this manner. N minus 1 by n into n minus 2 by n. And then you can further break this down. 1 by 3 factorial into this bracket can be written as 1 minus 1 by n. And this bracket can be written as 1 minus 2 by n. So this is what makes my third term in the next step. And similarly, you can write this fourth one as well. This is how you do it. So now, notice that 1 plus 1 by n, 1 minus 1 by n, this thing, it has, yeah, this thing is less than 1. This thing is less than 1. This thing is also this. All these terms are less than 1 because you're subtracting something from 1. Okay, 1 minus 1 by n, 1 minus 2 by n. So this entire summation, it will be less than 2 minus 1 by 2 factorial plus 1 by 3 factorial plus, and so on. Sorry, this plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial and so on till 1 by n factorial. So the entire summation S is less than this summation because each of these yellow shaded things is less than 1 in magnitude. Okay. So now finally, what is this thing? Now n factorial is greater than or equals to 2 to power n minus 1. Okay, so what I have is that 1 by 2 factorial. 2 factorial is greater than 2 to power 1. Okay, 3 factorial, which is basically 3 into 2, is greater than 2 into 2, which is basically 2 square. 4 factorial, which is basically 4 into 3 into 2, is greater than 2 into 2 into 2, which is basically 2. And so on. So what I basically end up with is the entire moral of this story is that n factorial is greater than 2 to power n minus. So this is what's written. So for all positive n values, this thing is greater than or equals to 1. So n is greater than or equals to for all n greater than or equals to 1. So this entire thing, so you can now reverse this. So 1 by n factorial will become less than 1 by 2 to power n minus 1. Right? Okay. This is 1 by n factorial is less than 1 by 2 to the power n minus 1. So now, as a final thing, what we do is we replace these terms. Okay, so what I've done is I've shown that my sequence 1 plus 1 by n to the power n is less than 2 plus 1 by 2 factorial plus 1 by 3 factorial and so on till 1 by n factorial, which is going to be less than 2 plus 1 by 2 to power 1 plus 1 by 2 to power 2 plus 1 by 2 to power 3 and so on till 1 by 2 to power n minus 1. Now this entire thing, it sums up to 1 by 2 to power 1 by 1, sorry. This entire thing will actually be less than 1. This part, just this part. This part is less than 1. Even if this goes to infinity, even if this goes till infinity, in that case, it will be equal to 1. This is basically 1 by 2 plus 1 by 4 plus 1 by 8 and so on. Right. So this thing is going to be equal to 1. I'll just show you in like 15 minutes why this will be equal to 1. I should actually have kept this example after after doing geometric progression. But yeah, after doing GP in like 15 minutes, we can appreciate the fact that this thing is actually equal to 1. So what I have is that this summation is always less than 1. So 2 plus something less than 1 will always be less than 3. Now, what was the purpose of this entire exercise is to show that my even if n keeps on increasing, even if goes to infinity, even in that case, this thing will always be less than 3. So I've shown an upper bound for this sequence. The sequence terms, no matter how large the n is, even if this goes on till infinity, this entire thing will always be less than 1. So this complete thing will always be less than 3. So the sequence is bounded up, it has an upper bound. All right. Also, it has a lower bound. It can never be less than 1, right? It can never be less than 2 actually. So this has a lower bound also, that it is always greater than 2. It can never be less than 2 because everything which comes after 2 is positive, right? Look at this. Everything that comes after 2 is positive. So it will always be 2 plus something. So what I have is that this sequence is always less than 3 and it is always greater than 2. So it is bounded. So my sequence Sn, which is 1 plus 1 by n, is bounded. So remember the theorem. The theorem says that if sequence is bounded and monotone, then it converges. So now I need to show that it is monotone increasing. So how do I show that it is increasing? So to show that it is increasing, look at this thing. As n keeps on increasing, this thing, right? Focus here. Why is this thing increasing? So as n increases, the number of terms increase, right? For small n, you will have just for n equals to 1, you will just have this. For n equals to 2, you will just have these 2 terms. For n equals to 3, you will have just these 3 terms. So as you keep on increasing n, the number of terms, they keep on increasing. At the same time, what happens to this number as n increases? Okay, so just focus on 1 minus 1 by n. As n increases, 1 minus 1 by n, will it increase or will it decrease?
It will increase.
It will increase because 1 by n reduces. as n increase, but so minus 1 by n reduces. So you're subtracting a smaller number from 1. So this thing will also increase. So the number of terms increases, plus each term becomes larger and larger as you keep on increasing n. So you're adding more terms and every term is larger. So as you keep on increasing n, the terms keep on getting larger and larger. So basically 1 plus 1 by 4 to the power 4 is greater than 1 plus 1 by 3 to the power 3. That's what I'm saying, that when you keep increasing n, the terms are going to be larger. So it's going to be a monotone sequence and it is bounded between 2 and 3. So I have a monotone bounded sequence. So this will be convergent. So in fact, what happened is this was like an open question. I think Aristotle or somebody posted this question, and then like a long time later, Euler gave the proof to this theorem, that this theorem is convergent, and the limit of this the sequence actually came to be known as E. E is the base of the natural logarithm. So if you can remember, now I don't want you to remember the proof. That is not important. What is important to remember is the steps. Like if you look at this proof, you should be able to understand, okay, this is what's happening. Okay, so next time, maybe 3 months from now or 6 months or maybe a year from now, when you're just revising the notes for exam, please don't be like, "Theek hai, sir ne bola tha, ye proof nahi aayega." Don't be like that. Go over the proof. See if you can understand these things, because being able to understand such complicated equations is going to be part and parcel. It might look complicated now, but I'm sure with 1 year of practice, things like these will become bread and butter. But practice is important. So that's why I keep doing these things. Okay, I can avoid these complicated stuff. I don't like scaring you guys. But the thing is, it's not scary because it's not going to be asked in exam. But so don't be afraid of it. Don't be scared कि ये सब करना पड़ेगा exam में. But you should be able to understand. Okay, and the steps here are beautiful. Okay, so how we are doing. So these are simple things which we know. Okay, if you look at the individual parts of this proof, the individual parts work like this. Okay, 1 minus 1 by n, it is increased. This is simple. We are using these small, simple steps to construct a whole proof, which by itself seems very daunting. But when you break it down into parts, it feels very doable. So this is the proof that 1 plus 1 by n to the power n is convergent. Now it is possible that in some exam they directly ask you this. Okay, they can directly ask you this question, that which of these sequences is convergent, and one of the options would be minus 1 to power n plus 1. They can give you 1 by n. They can give you 1 plus 1 by n to the power n plus to the power n. Okay, so they can give you this, and some other fourth example, they can ask you how many of these are convergent. So the answer would be this is convergent, this is convergent, this is not convergent. Okay, so they can ask you questions like this. So they'll never ask you to prove this thing, but they can ask you it as an objective, because it's a very popular sequence. It's math history. This question is the history of maths. Okay. became E. This equal, the limit of this sequence is. Now let's look at series. So series is the sister concern of sequences. So sequence is just the numbers. When you add the numbers, it becomes a series. But the summation has to be infinite. It cannot be finite because the series itself is infinite. So the summation of all the numbers of a sequence is technically called as a series. Now, usually we deal with finite series also, like we add 10 or 15 terms only. So that's called a finite series. But in common parlance, we don't really differentiate between a series and a finite series. Everything is series. Okay. So the examiner asks you to sum 10 terms of the series. It means that take the first 10 terms of the series and you add them up. So sometimes sequences are important, sometimes series is important. Suppose you are looking at inflation, it is the exact number which makes sense. But if you are looking at, let's say, your bank account or your bank account, suppose you are adding some amount every year. Okay, every year you are adding some amount in the bank account. So suppose you save amount S1 in period 1, S2 in period 2, S3 in period 3, and so on. So they can ask you like what is going to be the amount in your bank account after 20 years. So that's going to be the sum till 20. So you're just going to add up all these. So that's your series, first 20 terms. Okay, so we'll look at some popular types of series, and that's going to be about this chapter. I don't think we have much left. Yeah, just a couple of more pages and then we'll be done. So arithmetic series or arithmetic progressions are ones in which elements are adding by a constant difference. The difference is constant between different terms. For example, 1, 2, 3, 4, 5, 6, and so on. So you see the difference between these two terms is 1. Between these two terms is 1, 1, 1, 1, and so on. So this is an arithmetic progression. Okay. Here we see the difference -3, -3, -3, -3. So this is also an arithmetic progression. So arithmetic progressions are ones in which you keep adding the same amount after every term. Okay, the difference between any two terms is the same basically. So if you want to sum the n terms of an arithmetic progression, how do I do it? So suppose I want to find sum to first n terms of an arithmetic progression with the first term a. So generally we assume the first term is a and the common difference is d. So the nth term, this is the first term, this is the second term, this is the third term, and so on. So the nth term is going to be a plus n minus 1 times d, not nd. This is a common mistake we do. The nth term is going to be 1 plus n minus 1 nd. Okay, because just like the second term is not a plus 2d, the second term is a plus 1d. Third term is a plus 2d. So the nth term is a plus n minus 1. So I have to add them. So how do I add them? So I always recommend remembering formula if you can. Okay, but if you can't, then I'm just going to show you the proof. Maybe this will come in handy if you happen to forget the formula. Okay, so this is the sum S. Now let us reverse this order and write this again. So sum S is also a plus n minus 1 times d plus a plus n minus 2 times d plus so on till a. Now what is a plus n minus 1d? So this is going to be equal to 2a plus n minus 1 times d. What is this plus this? This is also 2a plus n minus 1 times d. And what is this plus this? This is also 2a plus n minus 1 times d. So this entire thing should be equal to s plus s, so that is 2s. So what you get is 2s equals to, there are n such terms. So n times 2a plus n minus 1 times d, right? So s equals to n by 2 into 2a plus n minus 1 times. Now, if you can remember this formula, great. If you can't remember it, at least remember this thing so that you can derive it in an exam. But obviously, when you do a lot of problems, it will stick to your head. So that's what we'll do. I'll be giving you a set of problem sets, and to practice it out, you can basically be more familiar with the formula. So that is the sum to first n terms of an arithmetic progression. Now, arithmetic mean, what is the arithmetic mean? It's the mean of any two numbers. So if you have numbers a and b, a plus b by 2. Now, arithmetic mean of n different numbers is summation divided by n. It's basically average. Okay, average is nothing but an arithmetic mean. So you don't have to, like, okay, what's the difference between average and arithmetic mean? There is no difference. It's the same. Okay, so this was arithmetic progression where the difference is constant. Next is geometric progression where the difference is always a multiple. Okay, so an example of this is in recent times COVID cases. So there was a huge talk about R0 being equal to 1.2 or 1.8, something like this. So what is the meaning of R0? R0 is basically the number of people who will be infected next fortnight. So if you have an R0 value of 1.2, what happens is that in 2 weeks, suppose you have 100 cases right now, in 2 weeks you will have 1.2 into 100 cases, which is basically 1200 cases. 120 cases. Okay, so this is R0 1 point. So you might have seen this number crop up somewhere in some article. So the number of COVID infections usually follows a geometric series. All right. So in geometric series, all numbers get multiplied by some constant thing every time. So this is multiplied by 3, then multiplied again by 3, then again by 3, and so on. So this is geometric series. We generally represent the first term as A, the next term as A into R, where R is called the common ratio. Next term is AR square, AR cube. So the nth term is AR to power n minus 1. Now suppose I want to add the first n terms of a GP. So I'll follow a similar pattern. So the first n terms sum is going to be A plus AR plus AR square plus AR to power n minus 1. Now what I'll do is I'll multiply this entire thing by R. So what I'll get is RS equals to AR. Okay, the first term becomes AR, but I'm not writing it here. I'm writing it here. Why? Because you'll see in a minute. AR square, so on. The term before this used to be AR to power n minus 2. That one became AR to power n minus 1. Okay, the term here, it became this. And this term, it became AR to power. Now what I'll do is I'll subtract the second equation from the first equation. So what I'll get is S minus RS is equal to, this cancels, this cancels, this cancels, just A minus AR to power n. Which means that A times 1 minus R equals, sorry, S times 1 minus R equals to A times 1 minus R to power n. So what I'll get finally is that sum is A into 1 minus R to power n upon 1 minus R. Okay. So let's do a simple example. Suppose in week 0, there exist 100 COVID cases and R0 value is 2. That is, everybody infects 2 different people. So if I am infected today, 2 weeks later, I'll be cured, but 2 different people would be infected by me in 2 weeks. Okay. So find total active cases and total infections. Total infections is all infections from the start of time. After 10 weeks, that is roughly 2.5. So that is the question. Okay, so you have a R naught of 2, which means that if every 2 weeks, the number of cases double. So week 0 is starting point, week 0, and I am interested in week 10, after week 10. And R naught is calculated for 2 week period, not a 1 week period. It's calculated for 2 weeks. Let me open this formula for you. Yeah, use this formula.
So 51,200.
Okay. So Vinay's answer is what is it? Total active cases or total infections?
Total infections.
Total infections. So let's just report total infections. Just forget total active cases. Just find total infections after.
So 102300.
Who was this?
Kanishka. So no, total active cases is same 51200 and total infections is 102300.
Okay. I think Vinay reported this as total infections. Let's see.
I'm getting total infections as 102400. No, 102300. Yeah.
Okay, so you're getting the same as Kanishka.
So what is the difference between total active cases and total infections?
Total active cases is, I'm assuming that if people who get infected, like I'll be cured after 2 weeks. The other guy, I'll be either cured or dead after 2 weeks. The two people I infected, they'll be the active cases. So after
Okay.
2 weeks, total active cases will be 200. Total infections would be 300 because I got infected in the past, right? So I'll be counted. I'll still be
Okay.
counted.
Makes sense. Thank you, sir.
So you usually see these two things being reported. Right? These two things are the most often reported statistic about total active cases, total infections. Okay, let's look at this thing. So I'm going to take A equals to 100 because I'm starting with 100. I'm going to take R equals to 2 because things double with 2. And N will be equal to 6. Why is it going to be equal to 6? This is the important thing. All right. Because if I take week 0 as N equals to 1, right? So the problem is if you are applying this formula, everything should be bang on. Okay. You cannot mess up the N. You change the N, you'll get a different answer altogether. So you cannot mess up the N. So N has to be bang on. So you cannot do like 5 or 7 or something like that. It will give you a wrong result. 10, 11. So obviously I'm dealing with 2 week gaps. So week 0, week 2, week 4, week 6, week 8, week 10. So if this is your N equals to 1, 2, 3, 4, 5, 6. So if you put these 3 numbers in this formula, you'll get the answer right away. So it will be 100 times R to power 6. So it's 2, 4, 8, 16, 32, 64. So 64 minus 1 upon 2 minus 1. So that is 2, 4. No, wait, 32, fifth power, right? R to power n minus 1. Sorry, R to power n minus 1s. So it would be 32. So it would be 32 minus 1, right? Or 1 minus 32 by 1 minus 2. So you can make it whatever you want. So this should be equal to 3100. Right. So let's do it manually. If you are not convinced, let's check it manually if I did it right. So we 100, 200, 400, 800, 1600, 3200. Yes, I did something wrong. Where did I put that?
So N should be 10.
No, N is definitely not 10. I'm changing by 2 weeks, right? I told you 2 weeks. R naught is changed in 2 weeks. So 10 weeks is basically, I don't take the count after week 1. I take it after week 2, then week 4, then week 6, 8, and 10. So that's how I'm going to do it. Oh, yes, sorry. This is the mistake. R to power n ही होना चाहिए. R to power n. N was 6. So it has to be 6.
So,
Yeah.
so I still have doubted how you're taking n equals to 6.
Yeah, sure. So I'm saying that I take count every 2 weeks, after every 2 weeks. So R naught technically is defined as the number of people a person infects. And usually a person is infectious for 2 weeks. If you remember initial guidelines, it used to be 2-week quarantine. Why did we say 2-week quarantine? We used to say 2-week quarantine because it was assumed that a person is infectious for 2 weeks. So R naught was defined as the number of people you infect after 2 weeks. So why do you have to consider weeks? In fact, consider fortnights. So instead of 10 weeks, I could write it as 5 fortnights. A fortnight is 2 weeks, right? So now are you convinced that n is 6?
Yes.
Because
Sir.
now it would be fortnight 0, fortnight 1, fortnight 2, fortnight 3, fortnight 4, and fortnight 5. So those will be your 6 periods. instead of week 1, week 2, week 4, week 6, week 8, and week 10. Okay, so these are some small things in which you can make mistakes. So if a question from GP comes, here's the thing, everybody knows this formula. The thing is, execution of this formula will be the key. That you should be able to execute. Execution means you should get N bang on, you should get R bang on, you should get A correct, everything, all these numbers should be correct. Okay, so then when I add these all numbers up, adding them up, I'll get 63. So most of you maybe made this mistake of taking n equals to 10 or 11. That's why you got such huge numbers. But that numbers are also insight into how large this could be if you look at a horizon of 20 weeks. So in 20 weeks, the 100 cases could become 1 lakh cases. Okay, with a simple R0 of 2. It was not 2 actually, it was something like 3, 4 back in April. So that's how exponentially it was. All right, so that is your geometric progression. Now the next thing is infinite geometric progression. So the sum to n terms is a into 1 minus r to power n upon 1 minus r. Right. Now if r is less than 1, okay, then limit n tending to infinity r to power n. If r is less than 1, then as n keeps on increasing, this r to power n will be 0. Right? Take r equals to half. So what are r powers? 1, 1 by 2. Okay, for r to power 1, r to power 2 would be 1 by 4, 1 by 8, 1 by 16, 1 by 32, and so on. So as you can see, this number is going to 0 as you keep increasing it. So this thing is going to 0. So now, since this limit is 0, you can say that S infinity equals to A upon 1 minus R, because this thing becomes 0. But this applies only when R is less than 1. So when you have an infinite summation, the numbers add to a finite thing. So suppose I am adding all these numbers up. Suppose I am taking A equals to 1 and R equals to half. So my numbers become 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 and so on till infinity. Even though the numbers are infinite, each is reducing. Okay. So to understand why this is becoming 1, imagine a bucket. So imagine a bucket. Let me take a perpendicular bucket. Sorry, I'm not done. I like these small things. Anyway, so there's this bucket. So what you do is every time you fill half the bucket. So you start with an empty bucket, you fill half of it. Then you again fill half of it. Then you again fill half of it. Then you fill a further half of it. You're never filling the bucket. You only fill half the gap which is remaining in the bucket. So first you fill it till 50%. So you see that 50% is done. The remaining 50% you fill half of it. So you fill it till 75%. The next time 25% is filled, so you fill only the half of that. So you fill till 87.5%, and that is how you. So if you keep on proceeding in this manner, the bucket will never get filled completely. You'll never be able to fill the complete bucket. Right. So even though you keep on doing this till infinity, the bucket will never run out of space. It will never spill water. So this is essentially what you are doing here. You're filling half, then the half of the remaining, then half of the remaining, then half of the remaining, and so on. So the sum total here, even if you go on till infinity, will only be equal to this entire sum. Okay, so that's how you can maybe relate to it. Why even if this goes on till infinity, the sum is never actually even equal to 1. Okay, so that's infinite geometric progressions. So these are some, this is an example. I'd like to discuss this in the next class. So try your hands at it. Work something, okay? Keep working on it, write something. Okay, obviously it's not very straightforward, but try to like take 7 common, add or subtract something, work something out. Maybe you'll find something. Okay, it's an interesting one. This, please remind me to discuss this. All right. These are some special sums which you need to remember. Sum of first n terms, sum of first n squares, that is n into n plus 1 to 2n plus 1 by 6. This is n into n plus 1 by 2. And sum of first n cubes is just square of this thing, n into n plus 1 by 2 ka whole square. So that is n into n plus 1 square by 2. So you have to remember this. So maybe what you can do is, when you have a notebook for maths, reserve the last few pages for formulae. And just note down the formulae which I tell you that you have to remember, because by the end of it all, you'll have a lot of notes and you won't be able to revise all the notes in the end. So it would be better if you could just keep a formula sheet handy. Okay, next is an uncharacteristic series. So last two topics, yeah, we'll probably end punctually. So some uncharacteristic series. Okay, by the way, it goes without saying, these are your problems from KPGP. We'll discuss them in the doubt session this week. Uncharacteristic series are something which don't get classified as one of these series. So one of the very important series is summation 1 by n. So I know that 1 by n tends to 0 actually. But summation 1 by n, what happens to summation 1 by n? So if I add up all these numbers till infinity, going till infinity, will the sum be finite? Will it be infinite? What will happen to this? So this result is very important, that this series will actually go to infinity. This result is absolutely important to remember. It comes up multiple times. Okay, they don't ask it directly, it comes up indirectly. You'll see when you do past years, I'll point it out that ye bola tha maine. Okay. Even when we do something other than past years, some theorems, so this series is very important, summation 1 by n. So the proof is, it goes like this. I club things up, 1 plus 1 by 2. I club 1 by 3, 1 by 4. I club these 4. Then I club the next 8. Then I'll club the next 16 terms. Then I'll club the next 32 terms and so on. That's how I'll club them. Now, 1 by 3 plus 1 by 4. Okay, wait. 1 by 3 is greater than 1 by 4. Okay, focus on this. This implies 1 by 3 plus 1 by 4 is greater than 1 by 4 plus 1 by 4. So I'm adding 1 by 4 on both sides. So this bracket is greater than this bracket. Similarly, 1 by 5, 1 by 6, 1 by 7, they're all greater than 1 by 8. So adding these 4 is greater than these things. Right? So this bracket is greater than this bracket. And similarly, this bracket will be greater than this bracket. So the thing above is definitely greater than the thing below. Now, what is the thing below? Okay, so if you look at this thing below, 1 by 4 plus 1 by 4 is 1 by 2. This is also 1 by 2. This is also 1 by 2, and so on it goes. So you have 1 plus 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2 and goes on till infinity. So you basically have infinite times 1 by 2, which is still infinity. So this thing tends to infinity. So this term itself tends to infinity. So this thing is definitely greater than that. That's what we established here. So this thing, which is summation 1 by n, is also going to tend to. So summation 1 by n is going to tend to. That's very important. All right, one last thing, roots test, ratio test, sorry. So ratio test is something which you can use to find if some particular sequence is it going to diverge to infinity or not. So what you can do is you can just find limit n tending to infinity an plus 1 by an. Okay, so limit n tending to infinity an plus 1 by an. That is n plus 1th term and nth term. You can find its ratio at infinity. Now, if this ratio, if it is less than 1, then the series converges. But if it is greater than or equal to 1, then the series diverges. So let us consider two examples. Just be patient for another 5 minutes and we'll be done. Okay, so this is something which might come in handy with for you. So that's why I'm doing this. So consider two sequences. One is 1 by 2, 1 by 4, 1 by 8, and so on. So this sequence is basically 1 by 2 to power n. And another sequence is 1, 1 by 2, 1 by 3, 1 by 4, which is basically 1 by n. So what I have to do is I have to find limit a n plus 1 upon a. Now n plus 1th term is 1 by 2 to power n. Nth term is 1 by 2 to power. So this is going to be equal to 2 to power n upon 2 to power n plus 1. So that is 1 by 2. So this is less than 1. Whereas when I look at this thing, this is going to be limit n tending to infinity. A n plus 1 is going to be 1 by n plus 1 upon 1 by n. So that is going to be equal to n upon n plus 1. Now I know I've not done limits, but if you can remember, what is limit n tending to infinity n upon n plus 1? Does anybody remember limits? Okay, the way to do it would be to just divide numerator and denominator by n. So this becomes 1 upon 1 plus 1 by n. Now 1 by n is 0. As n goes to infinity, 1 by n is 0. So this is just 1. So limit n tending to infinity, an plus 1 by an is 1 here, and this is less than 1. So what the ratio test tells is that if this ratio at infinity, if it is less than 1, then it converges. But if it is equal or greater than 1, then it diverges. And that's what we saw, right? We saw that this summation, this summation is convergent, whereas this summation is divergent. Okay, so that's your ratio test, might come in handy. So make it a point to revisit this ratio thing after we do limits. Okay, so sometimes things get front and back in maths, so we'll have to revisit some things after doing some data. That's how we'll do it. That's how we can do it in the most efficient way. Okay. Coming to problem sets, obviously, apart from everything in the text, you're supposed to do the problems which are given in here. So there are two problem sets, sequences 1 and sequences 2. So you're supposed to do both of them. I'll take a doubt session if possible in this weekdays. For the past years of sets, I've shared the past years with you. So you can start going through the solutions for past years from there. Obviously, I have not solved everything. So everything is not available there. So the things which are not available there, or the things which you have doubt after going through the solutions, that those questions will be discussing. And if time permits, we'll discuss sequences. So maybe somewhere around Wednesday would be fine. Wednesday or Thursday, I'll let you know. Okay, so do these problems, and yeah, if you're feeling comfortable, you can do the past years also. Okay, so I'll end it at this, and I'll see you guys tomorrow for microeconomics. Okay, so ending the class now, guys.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Welcome all.
Thank you, sir.